Alright guys, this is pre-calculus 4.1.2. So today we're going to take a look at essentially the opposite of 4.1.1. So we have here 4 different graphs. Now what I want you to do first is to write down an equation that would have these same x-intercepts. So effectively, like I mentioned, the opposite of what we just did last time. So be careful that you look for where it crosses, what the end behavior is, and then how it's going to cross to. So like, does it bounce, does it wiggle through, stuff like that. And then once you've got that, go ahead and resume the video. Okay, so ideally we got a fairly simple equation for A, B, C, and D here, right? Not a huge deal. So this one would be like x plus 3 times x minus 2. This would be x plus 2 squared times x minus 1. This would be x minus 2 squared times x plus 2 squared times x minus 1 squared. And over here we would have x plus 3 times x to the third power because you have that wiggle through, and then times x minus 2. And then we should get those graphs there, which is great. But then we're going to, on E here, try and actually check these. So if we graph these on Desmos, let's take a look at what we end up getting. So that first one, I'll type it in before I show you guys the full Desmos. It's just easier on me that way. So if we have x plus 3 times x minus 2, right? So if I show you that, there we go. Okay, so we have this graph here, right? And it looks exactly like the one that we had on the graph, right? We even have the same point here where it's crossing at that's at 8, negative 2. So if I put the point 8, or sorry, negative 2, 8, it is on our graph like it is on the original. So this is a perfect copy there. So now let's try the second one. Let's try B. So B, we said that it needed to be, oops, I wanted to delete all that. It needed to be x plus 2 to the second times x minus 1, right? Then it needs to be negative to get it the right way up. So there we go. Now does that match? Well, on our graph over down there on the PowerPoint, we actually crossed the y-axis at 8, and here we're crossing it at 4. So we're going to have to change that in order to make it work. So what we're going to do is figure out how we can do that. Now, with something this simple, to go from 4 to 8, we're just going to double it, so multiply it by a 2, and that's going to be the actual answer. But we're going to try and figure out, well, what do we actually need to do mathematically to find out what that value should be. So I'm going to take this down for a second, and we're going to take a look at how we're going to do that. Oops, let me focus that for us. Okay, so we have y is equal to, it was x minus 2, sorry, plus 2 squared times x minus 1, right? So the way that we can change it to make it hit at the right point is by multiplying some number in front of it. Now if I put like a 2 there, it'd be twice as tall. If I put a 1/4 there, it'd be 1/4 as like tall. So we can kind of do that. But we're not always going to have it so easy where we are going from 4 to 8, or even knowing what our y-intercept is. So what we're going to do is take any point that we want on the graph other than one of our x-intercepts. So for instance, we couldn't use like negative 2, 0 or 1, 0, because those would just give us the statement 0 equals 0, which is a true statement but not a helpful statement, right? So I could choose any point here that I want. So I would try and choose one that's like a nice pretty intersection, or like here's a y-intercept. That's a pretty nice one to use as well. So let's go ahead and use that. So to do that, I'm going to say, well, that's the point 0, 4. So that's the x coordinate and the y coordinate. So I can plug in 4 for y and 0 for my x's. So I get 4 equals a times 0 plus 2 squared times 0 minus 1. Well, solving this out, I get a times 2 squared is 4. Negative 1 is just going to be negative 1. So then negative 1, or sorry, a negative 4 times a negative 1 is going to be 4 equals, oh, sorry, I made a major mistake here. This feels wrong. So what I need to do, look at the actual equation, not the equation that I made. So let's go back to the PowerPoint here. It crosses at 8, not 4. This is the one that I'm trying to find, not the one that I made. Okay. So back over here, this is an 8, not a 4. Okay, that makes more sense. Doesn't change much of anything else though, but it does change that. Okay, so then we get, this is just a negative 4a equals 8. So if I divide by that negative 4, I get that a equals a negative 2. Right, and that is going to be the value that I plug in for my a. So my actual equation of the graph would be y is equal to negative 2 times x plus 2 squared times x minus 1. Right? So if I go back to my Desmos now, and now if I change this to being a negative 2 as my a, it does meet the criteria. It does go where I need it to go. Okay. So hopping back over here, what I want you to do now is take a look at C and D and figure out what would you need to change the value of A to B in order to make it the correct statement. And feel free to use Desmos to help you out here to see if it's right or wrong. Okay, so on C, 1 second, let me pull this up. Okay, so on C, you should end up getting negative 3/4 as your A, and on D, it's just an A negative 1. So why we do that still on D is that negative 1 will just kind of shows that you don't even need to worry about the negative parts for the in B behavior, because when you solve for that A, it'll become negative if it needs to be, or it'll stay positive if it can stay positive there as well. So that's our kind of process here. So let's take this and try it out on number 23. So they're going to give you the description in words as opposed to a graph, but it's the same thing as we just did. So go ahead and pause the video, work through number 23, and then once you're done, come back here. All right, so if we did this, right, let me pull up my Desmos tab. Let you see my Desmos tab as well. Okay, so if we were to graph it, right, we should have gotten 1/3 times x plus 2 to the second times x minus 5. Right? So, and this is the graph that we end up getting, right? And we're trying to say, hey, does it actually go through the right point? And it does, so we're good. Awesome. I'll zoom out a little bit so we can see it better. So then we have this other guy. His name is, it's Gilbert, right? Yeah. So Gilbert says, if I pull this up, Gilbert says, hey, I got this equation, which is similar to ours, but what they did was they have a 4th power here, right? So what I want to do is change ours to kind of match that, right? So let's test Gilbert's and see if Gilbert's is going to do the same. So his is 127. So let's top over, oops, there we go. So we'll do 1/27, and then it's the same thing as we just had here. So let's do some copy paste, and then this is to the 4th power, raised to the 4th power. There we go. So again, looking at like ours, right? So they at all of the same points. So we have this point here, and then we do have the same intersection right here. Okay, so both of these meet these same criteria. We have the bounce here, we cross here, and we go through there. So we have two different equations which meet the right criteria. And in theory, we could keep on doing this, right? If I change this to being x to the 6th, I'd have to use a different value of a, but I could still make it work, right? So that's the kind of issue here, is we could have an infinite number of different graphs which still give us this. So what we typically do is we add a qualifying statement to all of these, which is, hey, we're looking for the equation with the least degree possible that still meets these criteria, because here is a 5th degree polynomial, this is a 3rd degree polynomial. We like these smaller ones versus the more complex ones if they still give us these same results. So quite often on these statements, you're going to see that qualifying statement of, hey, find the polynomial with the least degree possible that meets these criteria. It bounces here, it touches here, it goes through here, and stuff like that. Okay. All right. Oops. There we go. Okay. So then a little bit of closure here. So if we have this situation here, right? Let's first talk about how many different possible equations could we have that go through these 3 points and then go through that have these 3 intercepts and then go through the point -160. Well, there's an infinite number, right? Because I can just make my degree larger and larger and larger and larger and larger, and I could go to infinity and theoretically have an infinite number of graphs that all meet this criteria. So I could either keep adding more and more points to narrow and narrow down my options, but there's still going to be an infinite number which meet the criteria. So we're going to have to add that qualifying statement of the least degree possible. And that's the kind of big crux here that we're trying to kind of get across. Because while being able to get the equation from the graph's not too bad, when we do that, we also want to make sure that we have that qualifying statement of the least degree possible, so that we limit us to just the one kind of answer which we're actually trying to find. All right, so with that, here is our homework for 412, and I will talk to you guys next time.